Overall equipment effectiveness is a hierarchy of metrics developed by Seiichi Nakajima in the 1960s to evaluate how effectively a manufacturing operation is utilized. It is based on the Harrington-Emerson way of thinking regarding labor efficiency. The results are stated in a generic form which allows comparison between manufacturing units in differing industries. It is not, however, an absolute measure and is best used to identify scope for process performance improvement, and how to get the improvement. If, for example, the cycle time is reduced, the OEE will increase, that is, more product is produced for less resource. Another example is if one enterprise serves a high-volume, low-variety market, and another enterprise serves a low-volume, high-variety market. More changeovers will lower the OEE in comparison, but if the product is sold at a premium, there could be more margin with a lower OEE. OEE measurement is also commonly used as a key performance indicator in conjunction with lean manufacturing efforts to provide an indicator of success. OEE can be illustrated by a brief discussion of the 6 metrics that comprise the system. The hierarchy consists of 2 top-level measures and 4 underlying measures. The top-level metrics, overall equipment effectiveness and total effective equipment performance, are 2 closely related measurements that report the overall utilization of facilities, time and material for manufacturing operations. These top-view metrics directly indicate the gap between actual and ideal performance. Overall equipment effectiveness quantifies how well a manufacturing unit performs relative to its design capacity, during the periods when it is scheduled to run. Total effective equipment performance measures OEE against calendar hours, that is 24 hours per day, 365 days per year. The underlying metrics, in addition to the above measures, there are 4 underlying metrics that provide understanding as to why and where the OEE and TEEP gaps exist. The measurements are described below, loading the portion of the TEEP metric that represents the percentage of total calendar time that is actually scheduled for operation. Availability, the portion of the OEE metric that represents the percentage of scheduled time that the operation is available to operate. Often referred to as uptime. Performance, the portion of the OEE metric that represents the speed at which the work center runs as a percentage of its design speed. Quality, the portion of the OEE metric that represents the good units produced as a percentage of the total units started. Commonly referred to as first pass yield FPY. Calculations for OEE and TEEP. What follows is a detailed presentation of each of the 6 OEE/TEEP metrics and examples of how to perform calculations. The calculations are not particularly complicated, but care must be taken as to standards that are used as the basis. Additionally, these calculations are valid at the work center or part number level but become more complicated if rolling up to aggregate levels. Overall equipment effectiveness, OEE breaks the performance of a manufacturing unit into 3 separate but measurable components: availability, performance, and quality. Each component points to an aspect of a process that can be targeted for improvement. OEE may be applied to any individual work center, or rolled up to department or plant levels. This tool also allows for drilling down for very specific analysis, such as a particular part number, shift, or any of several other parameters. It is unlikely that any manufacturing process can run at 100% OEE. Many manufacturers benchmark their industry to set a challenging target. 85% is not uncommon. OEE is calculated with the formula, performance, quality, using the examples given below. Availability equals 86.6%, performance equals 93%, quality equals 91.3% equals, alternatively, and often easier, OEE is calculated by dividing the minimum time needed to produce the parts under optimal conditions by the actual time needed to produce the parts. For example, total time, 8-hour shift or 28,800 seconds, producing 14,400 parts, or 1 part every 2 seconds. Fastest possible cycle time is 1.5 seconds, hence only 21,600 seconds would have been needed to produce the 14,400 parts. The remaining 7,200 seconds or 2 hours were lost. The OEE is now the 21,600 seconds divided by 28,800 seconds, or 75%. Total effective equipment performance, where OEE measures effectiveness based on scheduled hours, TEP measures effectiveness against calendar hours, that is 24 hours per day, 365 days per year. TEP, therefore, reports the bottom-line utilization of assets. Loading. The loading portion of the TEP metric represents the percentage of time that an operation is scheduled to operate compared to the total calendar time that is available. The loading metric is a pure measurement of schedule effectiveness and is designed to exclude the effects how well that operation may perform. Calculation. Loading equals scheduled time/calendar time. Example, a given work center is scheduled to run 5 days per week, 24 hours per day. For a given week, the total calendar time is 7 days at 24 hours. Loading equals 71.4%. Availability. The availability portion of the OEE metric represents the percentage of scheduled time that the operation is available to operate. The availability metric is a pure measurement of uptime that is designed to exclude the effects of quality, performance, and scheduled downtime events. The losses due to wasted availability are called availability losses. Example, a given work center is scheduled to run for an 8-hour shift with a 30-minute scheduled break. Operating time equals 450 minutes SCHED or Euro 60 minutes and shutdown time equals 390 minutes. Calculation, availability equals uptime/available time. Availability 390 minutes/450 minutes equals 86.6%. Performance/productivity. The performance portion of the OEE metric represents the speed at which the work center runs as a percentage of its design speed. The performance metric is a pure measurement of speed that is designed to exclude the effects of quality and availability. The losses due to wasted performance are also often called speed losses. In practice it is often difficult to determine speed losses, and a common approach is to merely assign the remaining unknown losses as speed losses. Calculation, performance equals/operating time. Example, a given work center is scheduled to run for an 8-hour shift with a 30-minute scheduled break. Operating time equals 450 minutes SCHED or Euro 60 minutes and shutdown time equals 390 minutes. The standard rate for the part being produced is 40 units hour or 1.5 minutes unit. The work center produces 242 total units during the shift. Note, the basis is total units, not good units. The performance metric does not penalize for quality. Time to produce parts equals 242 units 1.5 minutes unit equals 363 minutes. Performance equals 363 minutes/390 minutes equals 93.0%. Quality. The quality portion of the OEE metric represents the good units produced as a percentage of the total units started. The quality metric is a pure measurement of process yield that is designed to exclude the effects of availability and performance. The losses due to defects and rework are called quality losses. Calculation. Quality equals / example, 242 units are produced. 21 are defective. 242 units produced, 21 defective units, equals 221 units, 221 good units/242 total units produced equals 91.32%, 6 big losses of OEE. To be able to better determine what is contributing to the greatest loss and so what areas should be targeted to improve the performance, these categories have been subdivided further into what is known as the Euro 6 big losses, a Euro unregistered trademark to OEE. These are categorized as follows. The reason for identifying the losses in these categories is so that specific countermeasures can be applied to reduce the loss and improve the overall OEE. The 6 loss categories can be calculated manually, but there are also a plethora of simple calculators online. OEE is a heuristic. OEE is useful as a heuristic, but can break down in several circumstances. For example, it may be far more costly to run a facility at certain times. Performance and quality may not be independent of each other or of availability and loading. Experience may develop over time. Since the performance of shop floor managers is at least sometimes compared to the OEE, these numbers are often not reliable, and there are numerous ways to fudge these numbers. OEE has properties of a geometric mean. As such, it punishes variability among its subcomponents. For example, 20% 80% equals 16%, whereas 50% 50% equals 25%. When there are asymmetric costs associated with one or more of the components, then the model may become less appropriate. Consider a system where the cost of error is exceptionally high. In such a condition, higher quality may be far more important in a proper evaluation of effectiveness than performance or availability. OEE also to some extent assumes a closed system and a potentially static one. If one can bring in additional resources, then it may be more appropriate, for example, to use an expected net present value analysis. Variability in flow also can introduce important costs and risks that may merit further modeling. Sensitivity analysis and measures of change may be helpful. Automated OEE systems. Although OEE can be manually calculated based on collected production data, the standardization of plant floor networks and OPC technology has led many industrial vendors to introduce automated OEE systems, ranging in complexity from a single sensor to complex integrated MES, ERP or CMMS systems. Notable industrial OEE vendors include, recently there have developments in integrating auto-coding systems with OEE software, whereby OEE values can be displayed on operator screens. Further reading, Optimum FX Consulting, OEE in 6 Loss Explained, Calculation, Examples, Graphics, Optimum FX Ltda, Dwyer, John. OEE €1 The Great Energy Saving. The Manufacturer, 52 €, 55 France, Allon, Ithammer White Paper €, Implementing OEE Systems, Delivering on the Promise of OEE, Ithammer Systems Ltda, France, Allon, Ithammer White Paper €, The Business Case for OEE Systems, The Operational and Financial Return on Investment, Ithammer Systems Ltda, Hansen, Robert C. Overall Equipment Effectiveness. Industrial Press. ISBN A978-0-8311-3237-8. Koch, Arno. OEE for the Production Team. Makagami. ISBN A978-90-78210-08-5 ISBN 978-90-78210-07-8 ISBN 978-3-940775-04-7 Productivity Press Development Team, OEE for Operators, Overall Equipment Effectiveness, Productivity Press, ISBN A978-1-56327-221-9. See also, Total Productive Maintenance. References